Now that we have the concept of work down, we can start talking about energies, since work is, after all, transfers of energy. The first one we're going to talk about is kinetic energy. Consider a system that consists of a single object of mass m. Let an external force F push the object through a displacement d and ignore friction and drag for the moment. Then the work done by the force, which is always the change in energy of the object, is the change in the kinetic energy, because all the other energies are remaining constant. That is to say that the work, which is delta E, is now delta K, which is the final kinetic energy minus the initial kinetic energy, because that's just what delta means. There's nothing special there. But recall from kinematics that the final velocity squared is the initial velocity squared plus 2 times the acceleration times the displacement. Of course, we know from second law that A is F over m, and in our particular case, delta x here is the distance it traveled. So if we put all that stuff in, we get this equation. Then we do a bit of algebra. It's just algebraic arrangement, and we say, let's solve this over for, in this case, FD by cross-multiplying by m over 2. And I get FD is 1/2 mvf squared minus 1/2 mvi squared. The stuff on the left is just the work, which we know is delta K. So we have this thing is a thing final, something final minus something initial, and delta K, of course, is K final minus K initial. It makes sense to identify that K is 1/2 mv squared. The units of this K, would be 1/2 mv squared, a half doesn't have units, m times v squared, or kilogram times meters per second all squared, or kilogram meter squared per second square, which I could then factor out as kilogram meter per second square times a meter, or Newton times a meter, which is a joule. Of course, we knew it would have to be a joule, but this was a way of confirming that it's at least dimensionally correct to come up with this expression. This is technically the kinetic energy associated with the linear motion of the object, the fact that it's moving in a line. We call it translational kinetic energy. If the object is spinning, then there's kinetic energy associated with that. Things that spin also have energy. We call that rotational kinetic energy. But we won't consider rotational kinetic energy until we cover rotations, which is later in the class. Right now, you can skip that section. All right, let's do some problems. A two-man bobsled has a mass of 390 kilograms. Starting from rest, the two racers push the sled for the first 50 meters with a net force of 270 newtons. Neglecting friction, what is the sled's speed in meters per second at the end of the 50 meters? Now, the work is pretty easy. The work here is just going to be F times d, because the force is along the displacement. And so it's 270 newtons times 50 meters, which turns out to be 13,500 joules. But of course, that's not what we wanted. We were asked for a speed, and we're going to do that by saying, well, that's the change in kinetic energy. So the final kinetic minus initial kinetic energy. But starting from rest, we know that the initial kinetic energy was 0. So our final kinetic energy is also 13,500 joules. But we also know the kinetic energy is 1/2 mv squared. So Vf is square root of 2 times the kinetic energy over the mass. So we get square root of 2 times 13,500 joules over 390 kilograms, which turns out to be something like 8.3 meters per second. All right, a light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter starting from rest. After the force is removed, the kinetic energy of the light cart is which of the following compared to the heavy steel cart? A greater, B greater, B equal to, C less, or D can't say without knowing the magnitude of the force. They end up to be the same because they start with the same kinetic energy. They both start from rest, which is 0. And then they have the same force for the same distance, so the work done is the same. So the final kinetic energy is the initial kinetic energy plus the change, sort of duh. This is 0 plus the work done but the work is the same for both of them. Since the work is the same for both of them, then obviously so is the kinetic energy at the end. Some of the boxes shown, each of the boxes shown is pulled for 10 meters across a level frictionless floor by the force given. Which box experiences the greatest change in its kinetic energy? All right, well, it's the same distance. We know that the change in kinetic energy is the work, which is the force times the distance, but it's the same distance, so it's all going to depend on which one has the greatest force. The one with the greatest force is this one. Each of the 1 kilogram boxes starts at rest and is then pulled for 2 meters across a level frictionless floor by a rope with a noted force at the node angle. Which box has the highest final speed? Well, again, the final speed is going to be proportional to the final kinetic energy, well, square rooted. But a large kinetic energy will give us a larger final speed. They all have the same mass, right? So we don't have to worry about that part. The masses will be the same for all those. The final kinetic energy is going to be the initial kinetic energy plus the work, but they start from rest, so that's 0. So it's just the work, which is the force times the distance times the cosine of the angle. And the distances are all the same. So all that's going to matter is f cosine theta. All right. 10 times the cosine of 30, which is 8.3. We have 20 times the cosine of 30, which is, of course, twice as large, or about 17. Sorry, this is 8.6. This is 17.3. We have 10 cosine 45. That's something like 7.1. This will be twice as large, so it will be 14.1. And then we have 10 cosine 60, and that's going to be 5. So we see that it's going to be this one. Will give us the greatest kinetic energy and therefore the greatest final velocity.